Yeah, first of all, thank you to the organizers, Supratim, Sagar, Vishwesha, and Sandeep. Uh, I appreciate. And as Supratim already said, this is all the biology I know in the next half an hour. Uh, okay, so I hope this will be entertaining because I'm the guy standing between you and your evening plans. Okay, so I'm going to talk about adaptive diversification, how different species arise as the course of evolution. And essentially, yeah, this is the problem, origin of species. And even if we read Darwin's original text, he has glimpses of, I mean, he's giving his explanations, he's posing some very profound questions, how, so for example, these Darwinian finches, they occur on, in the same geographical location. And I mean, there are 10 million or so biological species. We saw about ants, but ants, mammals, whatever. So they are, and so if we believe, some of the theories, they have one common ancestor. So the question is that, how does so much diversity in nature occur? And what are the mechanisms for this speciation? Now, the question of origin of species or how does speciation take place, one of the explanations given is what I would refer to as geological, in the sense that, I have some traits or scalar phenotypes like the wingspan, the beak size, antibiotic resistance, and they get optimized in some environment. So, I mean, this looks more like rock formation or something at a, some geological process. So this looks very non-Darwinian in some sense, because that totally throws away the biology from it and attributes all the diversity we see or the biodiversity we see to some geology or something or some geographical niche. And any change in the phenotype at large time scales under this sort of assumptions is attributed to the abiotic environment. So, but then we have something like this. These are these African cichlids, which so many colorful fish exist in same geographical location like the lake. So the question is that how do they arise? And I'm going to be focusing on something called as sympatry or speciation arising in the same geographical location. And the driving force of this is going to be biotic interactions like competition, predation, which leads to a frequency dependent selection. And one of the consequences is that evolution is happening on these dynamic fitness landscapes, which are themselves function of the existing population. So it's a highly nonlinear, complex, dynamic phenomena, and as such, it's not sort of optimizing anything. Only thing we can talk about is some instantaneously what's happening, and the force of selection itself is changing with the phenotypic composition. So yeah, so that sort of is something I was able to get from the internet. So this is essentially what's happening, that there's a hill climbing, but what hill is to be climbed also depends upon the function of the population. So as the population tries to crawl on the hill, it's no longer the optimal solution. So, it just, these landscapes keep shifting like sand dunes. Okay, so, these are the basic assumptions theoretically. The minimal assumptions would be evolution is essentially a birth-death process with mutation and selection. And so this is, one agents-based model of some population where I have some mutations, and essentially what I am interested in is that as mutation, selection, birth, death happen, I'm interested in what sort of an evolutionary trajectory this sort of a population cloud takes place. So you can roughly imagine that this is the motion of the center of mass. This trajectory is the motion of the center of mass of the population cloud. So yeah, that is something I drew. So on the x-axis is my trait, which is it's the type of food, the size of the seed, and this black curve is the frequency of the food. that is like, at a particular side of the food, there's maximum frequency of that particular food. And this is the size of the beak. This is the population distribution of a species of one bird, and that's the beak size, so to speak. Now, the force of selection is going to make this population drift towards maximizing its chances of getting the most food. And essentially, what's going to happen is that so these are all hand-drawn, yeah, whatever. So the population is going to shift towards aligning itself with the maximum of food abundance. Is going to become narrow. And over here, when it comes over here, it has two choices. One choice is to just be there, so that would be something evolutionary stable. Or if there is the force of competition is disruptive enough, then the unimodal population is going to become bimodal or multimodal. And that's what I'm calling as mathematically what speciation is. So essentially, mathematically, the pattern formation of unimodal population going into bimodal or multimodal due to some biotic interaction, that is going to be my mechanism or mathematics of speciation. Okay, so yeah, so this is the same plot essentially. So over here, one thing about the tale of two fields, physicists try to minimize things and biologists try to maximize the fitness. It's the same thing essentially. So it's going to go, or you can imagine this to be like this. So the population try to reach some equilibrium due to the force of selection, and then this sort of a spreading happens, at least in one dimensions. Okay, so this was I've shown you a simulation of what happens in 2 dimensions, for example. So this is a simulation, an agent-based model where these guys had some food abundance and competition between them, and you immediately see that okay, now they are like 4 nodes to this thing. So it sort of diversifies into four things. So how do we make sense of that? So yeah, so these are some of the equations. So this is a logistic-like equation. Essentially, it tells you the growth of a population. X is the trait. The population is the function of the trait. Now, X can be a vector. This can be generalized to multi-trait. And this is essentially depending, so the per capita growth depends upon the existing population, and this term captures the competition because due to all the other constituents over here. So this logistic model takes into account both the biotic, which is the competition, as well as some sort of a carrying capacity. What's going to be the carrying capacity of the environment? So essentially, the role of adaptive dynamics in some sense is to extract out differential equations from an agent-based model so that we can do some analytics and probably predict some things. So one useful thing to be extracted out of this equation is something called as the fitness function, or what they call as the invasion fitness, which essentially is the growth, per capita growth rate of mutant X in a resident population of Y. So we saw in previous talks, that's how is one of the definitions of fitness, that how likely are the mutants going to invade the resident population. So this is, this is an important quantity upshot to look from these equations. And so what's happening? So as I said, this is an agent-based model. This is the adaptive dynamics trajectories out of that model. And to summarize, this was my fitness function. Okay, so the question is, what leads to evolutionary branching mathematically? So I have these 2 models, similar adaptive dynamics. The trajectory is the same, but the left shows no diversification at all. And if I see the right one, as I showed, it's showing adaptive diversification. So yeah, I wanted to notice one thing also. Also notice that, once there are 4 nodes, it sort of halts. There's some sort of a suspension in the motion, as well as the diversification. That might be something to look forward to, interestingly. So let's look at it, what's happening in one dimension. So as I said, this is the motion of the population cloud. It reaches some sort of an equilibrium. And then depending upon whether the extent of competition is outweighs the carrying capacity or the force or the central potential in some sense, which is making them coalesce, this is going to diversify. Mathematically, if you look at it, I Taylor expand the fitness function. So the first term just goes away. The fitness of x and x is 0. The second term gives me the selection force. This is something called as a selection gradient, which decides the force with which this population is moving towards its right, towards the maximum food abundance. And usually, if you notice, so this is going to be nearby infinitesimal mutation. So normally the second order term is not even important. All what happens when I'm not at equilibrium is that this first order term dominates and my population cloud just moves. At equilibrium, this term goes to 0, and it is the curvature, the second order derivative of the fitness function that kicks in, and that is causing possible diversification. So one of the necessary conditions for adaptive diversification in one dimension is that the population has to reach equilibrium. Yeah. Yeah. So food is sort of there, but the fitness depends upon the likelihood I can get food. Yes, that is. This is the side of the frequency of the seed. So those seeds are higher abundance. That's why the beak size is aligning itself to. Yes, but yeah, but then there are too many of us. So if there are more jobs in software, not all of us can get jobs in software. We have to diversify. So that's what I'm calling the disruptive force of competition, that all of us cannot do the same thing. But if we don't compete that much, then all of us probably can't do the same thing. So there are two things that play here. One probably decides by the environment, the size of the seed, and the disruptive force is the competition between us. So that's what I'm saying, that so depending upon this second order term, which is, and you can also see that the invasion is happening from both the directions. So depending upon the curvature of the fitness function, that will determine whether my disruptive force of competition is greater than what was aligning me due to the carrying capacity. Okay, yeah, so at equilibrium, this guy goes to 0, so then only the second order effects kick in. Yeah, so these are more simulations of agent-based models, how branching happens reaching equilibrium to 2 strands. And, I'll have now not only an adaptive dynamics of some tail coming from here, I'll have 2 different equations for these guys, and I'll have iterative evolutionary branching or adaptive radiation, as they call. This population bifurcates, then this guy bifurcates, then this guy bifurcates, and so this can keep going depending upon the model through the same process. Okay, so this is essentially the summary that ecological competition mathematically implies a certain curvature of the fitness function, which leads to evolutionary branching iteratively through many generations, which leads to adaptive radiation, which is essentially proliferation of many species across the environment. Yes. Yes. Oh, so essentially, I start with the population with, it's a birth-to-death process. So the birth rate is sort of neutral. Mutation can happen, the birth can happen through mutation. The death rate has selection, the guys with the lesser fitness are more likely to die. So the guys with the beak size towards the left will die. That's why the center of mass of the population over evolutionary timescales shifts to the center. So that's essentially happening. Okay, so yeah, so this was the story of one dimension where I had this the gradient factor which drive me to the equilibrium point, and this was the factor responsible for diversification. Okay, so essentially evolution happens in higher dimensional spaces. So in general, in higher dimensional dynamical systems, things can be typically chaotic, and there might not be any equilibrium point, so to speak. So, what happens to biodiversity? Because I saw in one dimension, I have to reach an equilibrium and then the curvature effect takes place. So, for example, this was, as I showed you, this was adaptive diversification in a two-dimensional model, which is, it's not in any equilibrium. Things are on a cycle and they are still branching out. So it's not coming to a rest and branching, it's sort of moving and sort of branching. Or I can have some sort of the motion on a Lorentz attractor, so to speak, which is a highly chaotic attractor. And depending upon the nature of my computation kernel, what's the extent of my computation, either I can, either I can, the population remains unimodal, or it can show interesting diversification as well as synchronized chaos, turbulent behavior, so to speak. So essentially, I mean, the explanation is pretty neat. So it turns out that I have to make the first order term 0. In higher dimensions, I really do not need to go to equilibrium to make it 0, because notice that the gradient higher dimension is a vector. And so is this displacement. So I just need these two vectors to be orthogonal to each other geometrically. And once these two non-zero vectors are orthogonal, this term can still vanish. That means that my first order effects are 0 despite not being on equilibrium. And then my curvature, which is now captured by the Hessian, kicks in. So geometrically speaking, this is the motion of my trajectory. Diversification can happen in an orthogonal plane, which would make sure that the first order things are 0 over here, but still the curvature effects will take place and the diversification is happening orthogonal to the trajectory it's going. Yeah, and what was my curvature is my curvature in high dimension, which is my Hessian. And essentially the necessary and sufficient condition for no diversification is that this matrix should be negative. Means all eigenvalues should be less than 0. Any eigenvalue being greater than 0, I mean, it's a stochastic process that might lead to some diversification. These things interestingly also depend upon the speed with which I'm going across a trajectory. Intuitively, even though it's a non-equilibrium process, the thing doesn't halt anywhere. But still, I feel that if I am on some sort of an equilibrium or a very slow moving point, then I'm more likely to diversify. I don't have a good mathematical argument for it, but that's what I was talking to Partha about, these tipping points where the speed of trajectories become very slow. It might have more propensity to diversify. That's just my intuition. Okay, so one more thing interesting over here is this, you can do this for higher dimensions. So I showed a two-dimensional thing. Now I'm showing an 8-dimensional thing and a 5-dimensional thing. And essentially, one interesting thing I noticed, remember I showed you this two-dimensional thing where I had this 4 populations, 4 species, and they sort of halted. This seems to be a generic feature where again, this is sort of, no motion is happening. They are just around. So what really happens when I simulate these things is that the population shows evolution, then it comes to a halt, and then it again shows evolution, it comes to a halt. So in some sense, the evolution is happening in spurts. It's not a gradual process, which I think there are experts in the field, they call it some sort of a punctuated equilibrium. That, when they see the fossils, they don't see a continuous evolution, they see evolution in spurts. At some time scales, evolutionary time scales, evolution is happening very rapidly. and at some time scales it's happening, it's halting, sort of speak. So maybe, these models can help understand microscopically through agent-based models what's happening as far as punctuated equilibrium is concerned. Yeah, okay, so now it started this. So this will halt. Yeah, trust me, it will halt. So, I mean, I showed you this many times, so it's not halting now. Yeah, now it halts. Okay, so, there are some interesting open questions that, the complete microscopic theory of punctuated equilibrium. One question which I was discussing with Sagar is that, really, these species, as I increase the dimensions, just the number of species increase exponentially. But, is there any mathematical structure to how many species with respect to a dimension I have? By dimension, I mean the dimension in the trait space, so to speak. And what's the long-term fate of these species? So, there are some new directions which I'll just throw in the ideas. So that'll be good to discuss. One question is that, is evolution predictable? Certainly I said that by definition, this evolution is happening in a very high dimensional space, and the high dimensional trajectories are typically chaotic, which shows an exponential sensitivity to initial conditions. So doesn't seem that evolution in general is predictive. Only in very controlled environments with working with very few trait types, the evolution might be repeatable or constructive. So this was captured by, so this I already showed you, the unpredictability or chaotic nature of evolutionary trajectories. This was captured by Stephen Jay Gould that, he said that if I am to wind back the tape of life, when, the life originated on Earth, will I get human beings again? That was sort of a philosophical question, but I mean, the evolution is happening in such a high dimensional space that on a chaotic trajectory, mutations by definition are random, quantum mechanical events. Unlikely I'll get human beings again. Yeah, so this was, if I mathematically analyze the adaptive dynamics equations, I can analytically as well as numerically show that as the dimension of my differential equations increase, I'm more and more likely to be, with probability 1, I'm more and more likely to get these trajectories as chaotic. There's some nice, I won't go into that, but essentially the instability and the instability of all fixed points is highly likely in a high dimensional phase space, so to speak. And this is how a typical trajectory would look like. Okay, so yeah, so till now I presented to you the approach of speciation through adaptive dynamics, which essentially is you take an agent-based model, you make some very nice assumptions, convert it into an initial value differential equation kind of a problem. But once I was in Dresden, and this pioneer of turbulence, Svitanovic, was giving a talk, and he said that the talk started with, do clouds solve the Navier-Stokes equation? That was the talk. So, we don't know what the heck is happening. We're just trying to model it in some way. So at a philosophical level, maybe there's a deeper statistical physics theory, which in some limit would yield to adaptive dynamics. But what turns to me into mind is that I don't have to look at these problems as initial value problems. Maybe some sort of a statistical mechanics, Monte Carlo approach, or this has all the elements of a grand canonical ensemble also in some sense. You have an open system with population increasing. You have a repulsive potential which is captured by population. So a totally radical approach to solving agent-based modeling, or rather than statistical Monte Carlo, might give us answer to some of these questions about so what's the long-term fate of the species, or how many species are there, so and so. Okay, so one criticism of this work is if you talk to people, it's still not airtight in the sense that all the competition kernels I showed you, which are actually showing diversification, I put them by hand in some sense. I mean, the biological assumption was very reasonable that like traits are likely to compete the most. if I and you have the same skills, we are likely to compete the most. But it's still an assumption. Uh, is there a way to go past that assumption? And I have some ideas from uh, actually quantum chaos literature, random matrix literature, where okay, I'll just take 2 more minutes. Okay, yeah, that this sort of a repulsion happens naturally when you see quantum chaos literature or something like that. So maybe there are some parallels over there. Uh, yeah, something interesting is happening for people interested in dynamical systems kind of work is that you see this was the motion on a Lorentz attractor. And as I increase the size of mutations, remember I told you that adaptive dynamics works in the limit of infinitesimal mutations. That's how I get differential equations. But in my agent-based model, as I increase the size of mutation, even on a chaotic attractor, this guy just goes to a fixed point. So there's some emerging stability the moment I relax the assumptions of adaptive dynamics. So that's something important. And lastly, I started the talk, I think there was the speed of evolution was in my title, it has come. So convince yourself that this movie is running slower than this movie. It's pretty obvious, right? So what I did was that, as someone asked a question, I changed the microscopic probabilities of the birth-death process over here. And the biological motivation for that can be that, if I have a most brutal competition, then it's no longer the usual way I simulate these agent-based models. I deterministically kill the weakest guy. So that's leading to essentially the same adaptive dynamics with speciation, but it's leading to adaptive dynamics with the higher speed. And I'm thinking about this thing. So this is sort of the, okay, this is not coming properly, but essentially, this is the underlying probabilities of the birth-death process, let's see. And this is my macroscopic observable, which can be the center of mass motion of the population cloud. Yeah, this equation is lifted from this paper. Of course, they don't do it for agent-based modeling, but does this equation remind you of something? It's very similar to the Ehrenfest theorem in quantum mechanics. Is also very similar. I mean, this is the expectation value of an observable. Here would come the commutator. Or in classical mechanics, this would be the Poisson bracket. And there are some very intriguing connections to how generically the motion of any observable in any theory, whether it's a stochastic theory or it's a quantum mechanics or classical mechanics, is going to take place. Essentially, what it's saying is that the motion or the speed of evolution is related to the correlation between the observable and I. So I here is just what they call the surprisal, which is the minus log of the probabilities. This is playing the role of, so these probabilities are the fuel of a birth-death process. They are taking the place of a Hamiltonian, which is the time evolution of a system in physics. So essentially, it's saying is that the speed of evolution is governed by how correlated an observable is to what's driving the evolution. And another term, if it is explicitly depends upon time. So there are some intriguing connections to both quantum and classical dynamical systems, or quantum physics and classical mechanics. And if you just step back and look, what the heck is a birth-death process anyways? I mean, birth-death process is creation and annihilation operators in your second quantization. You create a photon, you annihilate a photon, essentially. So there are some nice tantalizing connections which give me generalized speed limits of evolution, or quantum speed limits, so to speak. Yeah, so these are some of the directions. Yeah, so this is just a summary. Thank you.
necessary and sufficient condition of the Hessian
Yeah.
to be negative definite. So is it like I saw the form, it is something similar when the first order term is vanishing, it is similar to a quadratic programming maximization in which the function has to be concave. And then in that case also we get the Hessian to be negative definite. So are these two related, or it's completely out of the track?
Yeah, they could be related. See, I mean, so many things, as you know, the big brother Richard Feynman says, same equation, same solutions. So, so it would be interesting to see what, maybe there are some analogies to take from that into this. But yeah, I mean, Hessians occur all the time. And it just means that all eigenvalues negative means that I have blocked all the degrees where it could bifurcate. So, I mean, that's what's really geometrically, or, in other words, the higher dimensional curvature is not disruptive enough, so to speak.